And it's my great pleasure to present our UAF detection work. It's a collaboration with my co-authors, Jiang Ha and from ETI, Chu Hu and Teisu from Georgia Tech, and Zhiying from UC Riverside. Okay, so I guess that everyone here is very familiar with this kind of classic UAF problem, where the already freed memory could be accidentally accessed again by the dangling pointer, right? So people have known this kind of security issues and put lots of research efforts in it and researched it for a long time. So the interesting question is that why, after so many research efforts in automatically detecting such UAF issues, until today, they still remain the most dangerous and prevalent software vulnerabilities, right? So actually, if we look at this simple code snippet here, we can imagine that many existing static analyzers can very easily detect such issues given its clear pattern, right? So during our study, we found that in order to detect modern UAFs in large code bases like Linux kernel, we do have some significant difficulties, okay? So the first difficulty we noticed is that many UAF issues, they have use and free sets happen in different entry functions. So taking this as an example, right? So in the entry function 1, we have this object allocated at line 1, okay? And then it's freed at line 3. But the thing is that before it's freed, it gets escaped to a global pointer called GP. And then if we invoke entry function 1, we see that, okay, this object is fetched by GP and escape again to another global pointer called GQ, okay? And then if we finally invoke entry function 2, the same object will be accessed here within the entry function 2, causing a UAF. But the tricky part is that use and free happens in two different entry functions. And this creates many difficulties for existing static analyzers because they are unaware of such cross-entry alias relationship. Yet, these kinds of cross-entry UAF issues are very prevalent in complex code bases, like the multi-entry Linux kernel. Okay. So another difficulty we notice is that in order to validate a UAF issue, often the case we need to reason about many different code aspects. So take this as an example. We have introduced many mechanisms like lock, unlock, and pointer notification and condition recheck to potentially prevent this UAF issue. But if we inspect this case really carefully, we can see that the UAF is still possible. If we first try to invoke the entry function 0 and execute its critical section before we notify the global pointer GP, and then we execute the entry function 1. So at this point, we can successfully pass the condition check at line 8 because the GP hasn't got a chance to be notified yet, and its notification can happen too late, right? So to fix this bug, we simply need to swipe line 3 and line 4, and that's already a fix. But the tricky thing is that for many existing static analyzers, it's very difficult for them to discern the subtle differences here because they need to reason about so many different code aspects, lock, unlock, condition set, and check, right? Okay, so in this work, our goal is to develop a static analyzer which is capable of discovering such complex cross-entry UAF issues. We prefer this static method over the random fuzzing because it's more systematic. And as aforementioned, we need to tackle two major technical challenges. First one is that we need a way to precisely and efficiently identify such cross-entry alias relationship. And the second challenge is that we need to comprehensively take into account its multiple code aspects to validate the UAF. Okay, so our solution is called UAFX, and X here stands for cross. And this overall figure looks a little complex, but I will start from the very beginning part is input of our system, okay? So we require two parts as our input. The first part is the target program, where we need to discover the UAF issues compiled into the LLVM bitcode because our tool runs on the bitcode. And then we also require a configuration file which lists all the entry functions within the target program. Okay, so this configuration file could be semi-automatically generated, and more details could be found in our paper. So given all this target program and all its entry functions, let's reuse our previous example to show how we can first identify the cross-entry alias use and free pairs, okay? So our first step is that we perform a per-entry analysis to summarize all the important pointer flows and data flow facts. So in this case, for entry function 0, our summarization is that, okay, we know that the object will be freed at line 3, and it was allocated at line 1. Okay, and we also noticed that this object will escape to the global pointer GP. So this is our summary of entry function 0. And for entry function 1, our summary is that whatever object pointed to by GP will be fetched and escape again to pointer GQ at line 6. Okay. And then for entry function 2, our summary is that whatever object pointed to by GQ will be fetched and accessed at line 9. Okay, so this is our per entry function summarization. The example here is quite straightforward, but actually our implementation is quite accurate. We implement a inter-procedural flow context field and even opportunistically path-sensitive per entry summarization. More details can be found in the paper. Okay. So given all this per entry function summarized, our next step is that we can find this cross-entry alias use and free pairs with an efficient on-demand query. Okay, so by on-demand, I mean that we always start from the freed object. In this example, the freed object is this one at line 3. And given this freed object, we further query the per-entry function summary to find which global pointer it can escape to. And we found that it can escape to the pointer GP. Okay, and we recursively perform such on-demand query, and we found that this object can be further fetched by GP and then escape again to GQ. And eventually, our query brings us to the entry function 2, where we found that the alias object could be used and accessed. Okay, so at this point, we have identified a potential pair of UAF bugs, even though they are in the different entry functions. Okay, so our next step is that we need to verify that this UAF can really happen given the previous candidates. So towards this end, our first step is that we need to collect all the relevant program statements related to the UAF validation. Okay, for example, it's lock and unlock in the entry function 0 and in the entry function 1. But one important thing to note is that we not only need to identify these program statements within a single entry functions, we also need to carefully match them across different entry functions. So I mean that we need to know that the two locks in the different entry functions, they actually operate on the same lock object. And this is similar to our previous cross-entry alias analysis. So we basically follow the same procedure. First, the per-entry analysis, and then on-demand query to ensure that they operate on the same object. Okay. So similarly, for the condition set and check, we also need to ensure that the condition set at line 4, it will actually queue the condition check at line 8, which is in another different entry functions, because they operate on the same global variable. Okay, so we need to realize that they are conflicting set and check, and they are on the same global variable. Okay. So given all these relevant program statements, in order to validate the UAF, our next step is that we try to encode all these different code semantics into a unified partial order based system. By partial order, I mean the happens before relationship. So our observation is that all the different code semantics could be unified into this framework. If we consider semantics of lock and unlock statements, we know that these two critical sections cannot overlap. Okay, so we have either the line 3 will be executed before the line 7, or the line 10 be executed before the line 1. Okay, so this encodes the semantics of lock and unlocks. And similarly for condition set and check, because we know that we need to reach the line 9 to trigger the UAF. So the thing is that the line 8, the condition check, must happen before the conflicting condition set at line 4. Right? So we can also encode the condition set and check in this unified partial order based system. And of course, we also have some trivial constraints here, such as the line 1 must be executed before line 2. Okay, so this is nature intra-function constraints. So given all these constraints, we can employ a SMIT solver such as Z3 to find a solution. If a solution exists, in other words, there is a specific ordering of all these relevant program statements that can satisfy all our constraints, we say that UAF is feasible. And otherwise, we think it's infeasible case. Okay, so we implement our idea into our prototype system UAFX on top of our previous two Suture, but with quite some code modifications for our improvements and enhancements. And this tool will be fully open source at this GitHub link, which you can also find in our paper. Let me briefly introduce our evaluation results. Okay, so our first evaluation is about the bug finding capability. We assemble a dataset of no UAF bugs collected from the sysboard dashboard. And on this benchmark, we show that our tool can find significantly more real-world cross-entry UAF bugs compared to other competitor tools. Okay. And then we also try to find some zero-day bugs, and we run our tool against the 34 Linux kernel device drivers, and our tool successfully found 10 independent cross-entry UAF issues showing its value. Okay. And of course, accuracy is also very important. Regarding the false alarm rate, after we filter out all the highly similar false positives, eventually we can achieve an around 60% false alarm rate. This is comparable to many previous static bug detection tools for Linux kernel. And for the false negatives, I want to note that it's very challenging to evaluate it because we do not have the ground truth. But I want to note that we do intentionally introduce some false negative cases in order for a better false alarm rate. So specifically, we discard all the warnings involving the challenging reference count and the recursive data structures. Okay, so this inevitably introduces some false negatives. And for efficiency, the runtime of our tool varies, depends on the test subject. So for the most demanding Linux kernel device driver modules, it takes more than 30 hours to be analyzed. So in general, it's more expensive than many existing tools, but I think that partially it's because we target more complex cross-entry issues, and we also need to reason about many different code aspects. So in summary, I think the UAFX is valuable in helping the developers and the security practitioners find some tricky cross-entry UAF issues, but of course, there's a large room for us to continuously improve our efficiency and accuracy. Okay, so this is really a brief introduction of our project due to the tight time limit, but welcome to check our papers for more technical details, and I'm also happy to take any questions. Thank you so much.
We have time for a few questions. If you want, please go ahead to the microphone and ask a question. Okay, I'll start with the first one, maybe. Yeah, do you want to go ahead? Yeah, you always get the privilege. Go ahead.
Hi, Han. I appreciate your hard work. I'm Zhen Chuan from UC Riverside. I have read your previous work, Suture, which identified data flow bugs across multiple system calls. So I can see the connection of this work with that work. So I'm curious, how many more lines of code have you written to make?
So actually we have slides that show the code changes. I think roughly we have like 12K lines of code that we add to the previous tool. So this is mainly because that we need to implement a new cross-entry alias analysis mechanism, and also we need to implement that unified framework to filter out the false alarms. Okay, yeah. So this will be fully open source. So I do hope that this can help more people to develop the more static analysis to support more type of bugs. Yeah. Okay.
I had imagined you have written a lot more code for this because this would involve a lot of very hard-working details. So I would imagine you written a lot of work.
Yeah. It builds on top of existing tools. I think it's a typical workflow in the static analysis development. So usually people need to come up with lots of code, but hopefully with the latest generation of AI techniques, this task could be a lot easier. So for future implementers.
Thank you.
Yeah, thank you.
Hey, let's thank the speaker one more time.